The map units delineated on the detailed soil maps in this survey represent the soils or miscellaneous areas in the survey area. The map unit descriptions in this section, along with the maps, can be used to determine the suitability and potential of a unit for specific purposes. They can also be used to plan the management needed for those uses. A map delineation on a soil map represents an area dominated by one or more major kinds of soil or miscellaneous areas. A map unit is identified and named according to the taxonomic classification of the dominant soils. Within a taxonomic class, there are precisely defined limits for the properties of the soils. On the landscape, however, the soils are a natural phenomena, and they have characteristic variability of all natural phenomena. Thus, the range of some observed properties may extend beyond the limits defined for a taxonomic class. Areas of soils of a single taxonomic class rarely, if ever, can be mapped without including areas of other taxonomic classes. Consequently, every map unit is made up of soils or miscellaneous areas, major components, for which it is named, and some minor components that belong to taxonomic classes other than those of the major components. Most minor soils have properties similar to those of the dominant soil or soils in the map unit, and thus they do not affect the use and management. These are called non-contrasting or similar components. They may or may not be mentioned in a particular map unit description. Other minor components, however, have properties and behavioral characteristics divergent enough to affect the use or require different management. These are called contrasting or dissimilar components. They generally are in small areas and could not be mapped separately because of the scale used. The contrasting components are mentioned in the map unit descriptions. A few areas of minor components may not have been observed and consequently are not mentioned in the descriptions, especially where the pattern was so complex that it was impractical to make enough observations to identify all the soils and miscellaneous areas on the landscape. The objective of mapping is not to delineate pure taxonomic classes, but rather to separate the landscape into landforms or landform segments that have similar use and management requirements. The delineation of such segments on the map provides sufficient information for the development of resource plans. If intensive use of small areas is planned, however, on-site investigation is needed to define and locate soils and miscellaneous areas. An identifying symbol precedes the map unit name in the map unit description. Each description includes general facts about the unit and gives principal hazards and limitations to be considered in planning for specific uses. Soils that have profiles that are almost alike make up a soil series. All the soils of a series have a major horizons that are similar in composition, thickness, and arrangement. The soils of a given series can differ in texture of the surface layer, slope, stoniness, salinity, degree of erosion, and other characteristics that affect their use. On the basis of such differences, a soil series is divided into soil phases. Most of the areas shown on the detailed soiled maps are phases of soil series. The name of a soil phase commonly indicates a feature that affects use or management. For example, sandplat ashy loamy sand 0 to 15% slopes is a phase of the sandplat series. Some map units are made up of two or more major soils or miscellaneous areas. These map units are complexes or associations. A complex consists of two or more soils or miscellaneous areas in such an intricate pattern or in such small areas that they cannot be shown separately on maps. The pattern and proportion of the soils or miscellaneous areas are somewhat similar in all areas. Scoured juniper rock outcrop complex, 3 to 40% slopes is an example. An association is made up of two or more geographically associated soils or miscellaneous areas that are shown as one unit on the maps. Because of the present or anticipated uses of the maps in the soil area, it was not considered practical or necessary to map the soils or miscellaneous areas separately. The pattern of relative proportion of soils or miscellaneous areas are somewhat similar. Rubble land rock outcrop cliffs Emerald Lake Association, 25 to 150% slopes is an example. This survey includes miscellaneous areas. Such areas have little to no soil material and support little or no vegetation. Cinderland and lava flows are examples. Some soils are inextensive or have more variability than a soil series. These soils are named at higher taxonomic level than a soil series. These higher category soils have complete descriptions and data, but the ranges in characteristics may be broader than those of a soil series. Table 4 shows the component name and the map unit symbol or symbols in which the component occurs. It also shows the local phase, the component kind, and the ecosite ID to which the component is correlated per soil map unit symbol. The intent of this table is to help the reader understand the legend and the data structure of this soil survey and the specific correlations between soil components and ecological site descriptions. By cross-referencing the soil maps with this table, the reader can ascertain the geographic locations of soil components mentioned in the section Formation of the Soils. Table 5 gives the acreage and proportionate extent of each map unit. Other tables give properties of the soils and the limitations, capabilities, and potentials for many uses. The glossary defines many of the terms used in describing soils or miscellaneous areas. Figure 3 shows the location of figures 4 through 6, block diagrams 1 through 3. The block diagrams were produced from the detailed soil maps. Figures 4 through 6 illustrate the relationships of the detailed soil map units in the survey area to the geography, topography, geology, and climate in the area. The vertical scale of the diagrams is exaggerated 2 times in relation to the horizontal scale. This exaggeration helps to more clearly illustrate the topography of the area. The side walls of the diagrams are not to scale and are idealized to help illustrate the soil characteristics, soil parent material, and geology. The block diagrams are not intended to replace the detailed maps. Figure 4 is block diagram 1. This diagram shows the north-flowing glacial valley in the Manzanita Creek drainage. Multiple glacial episodes and ice levels shaped this valley, leaving traces of features such as glacial valley walls and floors, scoured lava flows, moraines, and outwash plains. The more recent glaciations were generally less extensive and cut into and deposited over pre-existing glacial features. Moraines and outwash plains form the gradient flattened beyond the confining bedrock of Lassen Peak and Loomis Peak. The active colluvial nature of Lassen Peak has shed many of the glacial features that were formed on it. Chaos crags erupted and was emplaced after glaciations, obliterating any glacial features that existed there prior to the eruption. Thick deposits of tephra were deposited around the vent dome A of Chaos crags and covered a large area of the northern part of the park with thinner deposits. A rockfall avalanche formed at the base of the unstable volcanic dome of Chaos crags. Debris flows from eruptions of Lassen Peak flowed off of the peak and were deposited in flat valley bottoms. Figure 5 is block diagram 2. This diagram shows the east-flowing valleys of Hot Springs Creek and Kings Creek drainages. Multiple glacial episodes and ice levels shape the valleys surrounding the terrain and form glacial valley walls, floors, scoured lava plateaus, glaciated volcanic domes, moraines, and outwash plains. Ice level fluctuations cause glaciers to override the drainage divide between the valleys, as well as exist as confined valley glaciers within the individual valleys. Outwash was deposited in the flat bottom of the U-shaped valley along the Hot Springs Creek. Spring activity and stream channel migration have partially replaced the outwash plain. Today, Kings Creek has larger watershed that originates at a higher elevation than Hot Springs Creek. The valley along Hot Springs Creek has a more pronounced U-shaped form than the valley along the larger Kings Creek drainage at this cross-section. This perceived contradiction could be due to the faulting and the presence of geothermal springs along Hot Springs Creek, and associated different features in the hardness and integrity of the bedrock. The complex nature of landscape evolution in this dynamic area is driven by the formation and destruction of volcanoes in conjunction with glacial fluctuation and relict features from previous landscapes which could have influenced today's features. Figure 6 is block diagram 3. This diagram shows a north-flowing glacial valley in the Grass Creek drainage and the surrounding glacial scoured uplands. Unconfined glaciers scoured the lava flows on the uplands and deposited till in the valley below as they merged into partially confined north-flowing glaciers. The glaciers did not completely cover Red Cinder Cone, Ash Butte, and Mount Hoffman. Red Cinder Cone and Ash Butte retained much of their cinder cone shape and composition, and Mount Hoffman formed a nunatak composed of remnants of the Ditmar volcano center. Outwash was deposited in the lower, flatter reach of the valley. The lake terraces are likely remnants of the fluctuations of a glacial lake. The lava flows from the cinder cone obstructed the drainage to form Snag Lake.